Welcome back. This is chapter 12 in Engineering Electromagnetics by Hayt and Buck. The title of the chapter is Plane Wave, Reflection and Dispersion. In this chapter, we are going to consider wave reflection and transmission at planar boundaries between different media. This reflection and transmission include the cases of normal incidence and oblique incidence. In the case of oblique incidence, the wave will be decomposed into transverse electric and transverse magnetic components. So, in the cases of oblique incidence, we will see transverse electric reflection and transmission coefficients and transverse magnetic reflection and transmission coefficients. In addition, we are going to study waves in dispersive media. Dispersive media is a medium which have some parameter which affect the propagation, and this parameter is varying with frequency. So what will be the effect of this frequency dependent propagation or frequency dependent propagation? What will be the effect of this frequency dependence on the shape of the wave through this media? So this is what we are calling waves in dispersive media. We are going to start with the reflection and transmission, and the simplest case is reflection and transmission due to normal incident plane wave. In this case, we are going to assume that we have two semi-infinite media, region 1 and region 2, where region 1 is characterized by electrical and magnetical parameters mu1, epsilon 1 dash and epsilon 1 double dash, and region 2 is characterized by electrical and magnetic parameters mu2, epsilon 2 dash and epsilon 2 double dashes. And we are going to assume that the two media, the interface between the two media is the xy plane. So the normal to the interface is the z direction. And medium 1 is extending from z equal minus infinity to z equal 0. And medium 2 is extending from z equals 0 to z equals infinity. We are going to assume that the incident wave is coming from region 1. So we have incident plane wave from region 1 in positive z direction. This incident plane wave is divided into two parts. One part is transmitted to region 2, and the other part is reflected back in region 1. So the transmitted part would be called the transmitted wave, and the reflected part would be called the reflected wave. The incident wave is assumed to be composed of electric field E1 plus and magnetic field H1 plus, and in this case E cross H should be satisfying that would be in the positive z direction. So assuming that the electric field in x direction and the magnetic field in y direction, so E cross H would be in positive z direction, so it would be in the direction towards the interface. Okay. For the transmitted wave, the wave will be propagating also in the positive direction. So in this case, we have E, the magnitude of the electric field, it would be E2 plus, and the magnetic field is H2 plus. And in this case, assuming that the electric field in positive x direction, the magnetic field should be in positive y direction, such that the propagation constant would be in positive z direction. For the case of the reflected wave, the situation would be different because the reflected wave would be propagating in negative z direction. So assuming that the electric field of the reflected wave is E1 minus in positive x direction, so in this case, the magnetic field H1 minus should be in negative y direction, such that E cross H would be in negative z. So it would be in the opposite to the incident wave. Effectively, the incident wave is a known value. The unknown values are the transmitted and the reflected waves. So our plan is to obtain the amplitude of the transmitted and reflected waves in terms of the incident wave. And because the magnetic field is related to the electric field by the intrinsic impedance, so H1 plus as a magnitude would equal E1 plus over eta 1, where eta 1 is the intrinsic impedance of region 1. Similarly, H2 plus would equal E2 plus over eta 2, where eta 2 is the intrinsic impedance of region 2. Finally, H1 minus would equal E1 minus over eta 1 in minus direction because it is in the negative z propagation. So it would be minus E1 minus over eta 1. So actually, we don't have 6 field components. We can determine all the parameters in terms of the electric field only. So we have E1 plus, E2 plus, and E1 minus. So it is required to find out the amplitude of the transmitted electric field in terms of the incident electric field and the amplitude of the reflected electric field in terms of the amplitude of the incident field. So our plan is to find out E1 minus as a function of E1 plus and E2 plus as a function of E1 plus. Effectively, the ratio between the amplitude of the reflected electric field to the incident electric field, E1 minus over E1 plus, we are going to call it the reflection coefficient. And the ratio between E2 plus to E1 plus, we are going to call it as the transmission coefficient. So our plan is to determine the reflection coefficient and the transmission coefficient, or in other hands, E1 minus in terms of E1 plus and E2 plus in terms of E1 plus. Okay? So in instantaneous form, the incident field EX1 plus can be represented as the amplitude EX10 plus multiplied by e to the power minus alpha 1z, the attenuation coefficient of medium 1, multiplied by cosine omega t minus beta 1z, the propagation constant of medium 1. In phasor form, we can say that the phasor of the electric field is the amplitude of the electric field EX10 multiplied by e to the power minus alpha z multiplied by e to the power minus j beta 1z. Or briefly, we can say that e to the power minus j k1z, where k1 is beta minus j alpha. Okay. Now, assuming that medium 1 is lossless, so in this case alpha 1 would be 0, so we are talking only about beta 1z. Okay, so This is a phasor form of the incident plane wave in terms of its amplitude and its complex propagation constant k. In a similar way, we can find out the magnetic field of the incident field in terms of the incident electric field as Hy plus would be Ex plus over eta 1, or eta 1 is the intrinsic impedance of medium 1, multiplied by the complex propagation constant e to the power minus j k1z, where k1 is beta 1 minus gr. Okay? k1 and eta are in general complex. Assuming that epsilon double dash 1 or sigma 1 is 0, so in this case k1 and eta 1 would be pure real. To simplify the problem, we are going to study the case of lossless medium at the beginning, and then we can generalize our solution to the case of lossy medium. The direction of propagation of the incident wave is perpendicular to the boundary plane. Here the propagation is normal to the interface plane. So that's why we are calling this type of incidence is normal incidence. So because it is perpendicular to the interface or normal to the interface, it is normal incident plane wave. Now we have described completely the incident field in terms of its electric field and magnetic field. What will be the situation for the transmitted and the reflected? We can represent the transmitted and the reflected field in the same way, such that the phasor component of the reflected electric field Ex S1 minus it would be the amplitude Ex1 minus multiplied by the propagation constant. Now the propagation constant would be in the negative z. So instead of e to the power minus jk1z, it would be e to the power plus jk1z. It is backward propagating wave. Right? The magnetic field in this case will not be in y direction, it would be in negative y direction. So in this case, Hy would be negative. The magnitude of the reflected electric field over the intrinsic impedance of medium 1, because effectively the reflected field lies in medium 1 as the incident field, but in opposite direction. And the propagation constant here is backward propagation constant e to the power jk1z. On the other hand, the transmitted wave, the phasor of the transmitted electric field Exs would be Ex2 plus multiplied by forward propagating wave in the second media. So it would be e to the power minus jk2. So this is a complex propagation constant in the second media, e to the power minus jk2z. And the magnetic field in this case would be in y direction, so it would be positive 1 over eta 2. Eta 2 is the intrinsic impedance of the second media, multiplied by the amplitude of the electric field Ex, multiplied by the forward propagation constant in z direction, e to the power minus jk2z. So this actually is the representation of the incident, reflected, and the transmitted waves. This representation or these representations are in phasor forms. Okay. Now, as we mentioned, we want to find out the value of the transmitted electric field in terms of the incident field and the value of the reflected field in terms of the value of the incident field. So we have two unknowns, EX10 minus and EX20 plus, and we have only the unknown value, or what we are going to take this value in terms of EX10 plus. So we have two unknowns. To obtain the value of these two unknowns, it is required to obtain two equations, and these two equations can be obtained by applying two boundary conditions. So the boundary conditions between two media, in this case, the electric field and the magnetic field, both of them are tangential component to the interface, because the electric field in X and the magnetic field in Y, and both of them are tangential to the interface between region 1 and region 2. So we are looking for the boundary conditions for the tangential components. So we have boundary condition for the tangential electric field, and we have another boundary condition for the tangential magnetic field. Each boundary condition will introduce an equation. So these two equations in the two unknowns, EX10 minus and EX20 plus, two equations in two unknowns, we can obtain the solution of these two unknowns. So by applying the tangential electric field boundary condition, the boundary condition of the tangential electric field states that E tangential 1 or E tangential at boundary at region 1 equal E tangential 2 at region 2. So the total electric field tangential to the interface in region 1 equals the total tangential electric field in region 2. In region 1, the total tangential electric field is coming from the incident wave and the reflected wave. So at the interface is Z equals 0. At the interface, we have incident wave equal EX10 plus multiplied by e to the power minus jkz, and z equals 0. So this exponential term is unity. This is the tangential component due to the incident wave. On the other hand, the tangential component due to the reflected wave at z equals 0 would be EX10 minus. So the total tangential electric field at the interface from region 1 would be EX10 plus EX10 minus. Or in other words, the amplitude of the incident wave plus the amplitude of the reflected wave. This is the tangential component at the interface at region 1. At region 2, the tangential electric field component would be EX2 plus multiplied by e to the power minus jk2z, and z in this case is 0 because the interface is at z equals 0. So this exponential term would be 1. So in this case, the total tangential component at the interface from region 2 is EX2 0 plus. So by equating the tangential field component at region 1 to the tangential electric field component at region 2, we say that EX total at region 1 equal EX total at region 2 at the interface z equals 0. The total electric field tangential at the interface at region 1 is Ex1 plus Ex1 minus the amplitude of the incident electric field plus the amplitude of the reflected electric field would equal the amplitude of the transmitted electric field. So in this case would be Ex10 plus Ex10 minus would equal Ex20 plus. So now we have a relation between the incident field or the amplitude of the incident field and the amplitude of the reflected field and the amplitude of the transmitted field. These are two unknowns in terms of the incident field. Now it is required to find another relation which combines these three components such that we can obtain E minus in terms of Ex10 plus and E2 plus in terms of Ex10 plus. The other relation is obtained by applying the tangential magnetic field boundary condition. So the tangential magnetic field boundary condition states that the total tangential electric field at region 1 minus the total tangential electric field at region 2 equal the surface current at the interface between region 1 and region 2. And assuming that we don't have surface current at the interface, so in this case the tangential electric field at region 1 minus the tangential magnetic field in region 2 would equal 0, or in other words, the tangential magnetic field in region 1 would equal the tangential magnetic field at region 2. And in this case, the tangential magnetic field at region 1 is composed of the magnetic field of the incident wave, because it is in y direction, which is tangential to the interface, because the interface is xy plane. So the incident magnetic field plus the reflected magnetic field, and it should be noted here the reflected magnetic field in opposite direction to the incident magnetic field. This would equal the transmitted magnetic field or transmitted tangential magnetic field, and once again the magnetic field here in y direction, which is tangential to the xy plane or the plane of the interface. So the boundary condition in our case is the total phasor magnetic field in y direction in region 1 equals the total phasor magnetic field in region 2 in y direction, because we don't have a current density at the interface. If we have a current density in the interface, so the difference between them would equal this current density. But fortunately, we don't have current density now. Okay? Alright. So the total tangential magnetic field at region 1 is Hy S1 plus, which is the incident, plus Hy S1 minus, which is the reflected, equal the transmitted in region 2, which is Hy S2 plus in region 2. And the magnetic field of the incident, reflected, and transmitted are related to the electric field by the intrinsic impedance as follows. Hy S1 it can be replaced by Ex10 plus over eta 1. And Hsy minus, the reflected magnetic field, it can be replaced by minus Ex10 minus over eta 1. And finally, Hy S2 plus can be replaced by Ex2 plus over eta 2. So this is the second relation between the amplitude of the incident electric field, the amplitude of the reflected electric field, and the amplitude of the transmitted electric field. Now we have two equations in two unknowns. So now this is the first equation which was obtained from the tangential electric field boundary condition, and this is the second equation which was obtained from the tangential magnetic field boundary condition. Now it is required to solve these two equations simultaneously. First of all, we can remove the value of the transmitted electric field by replacing it here. Ex2 plus can be replaced by eta 2 multiplied by these two components, and these two components include the incident and the reflected, and here is the incident and the reflected. So we can find a relation between the incident and reflected field only by eliminating the transmitted electric field component. So by multiplying this equation, the two sides of this equation by eta 2, and replacing Ex2 plus by eta 2 multiplied by Ex10 plus over eta 1 minus eta 2 multiplied by Ex10 minus over eta 1, we obtain this relation. Now, this relation is a relation between the incident field and the reflected field only. So we can arrange it such that the reflected field, the value of the reflected field Ex1 minus, by getting this term in this side and getting this term in this side, we can say that Ex10 minus the amplitude of the reflected field equal the amplitude of the incident field multiplied by eta 2 minus eta 1 over eta 2 plus eta 1. As I said, we are going to move this to this side, so it would be Ex10 minus multiplied by 1 plus eta 2 over eta 1, and here we move this to the other side, so it would be Ex10 plus multiplied by eta 2 minus eta 2 over eta 1 minus 1. So in this case, this would be eta 2 minus eta 1 over eta 1, and this would be eta 2 plus eta 1 over eta 1. So we can find out this relation. Now we succeed to obtain the value of the reflected field in terms of the value of the known incident field. So this unknown value in terms of this known value. Or in other words, we can define the reflection coefficient as the value of the reflected electric field to the value of the incident electric field Ex minus over Ex plus. It would be eta 2 minus eta 1 over eta 2 plus eta 1. Is that what we are seeing? We are going to define the value of the reflected electric field to the value of the incident field as gamma, where gamma would be defined as the reflection coefficient, and in this case it would be eta 2 minus eta 1 over eta 2 plus eta 1. For general lossy media, eta 2 and eta 1 are complex values. So these are complex values over complex value. So in general, the value of the reflection coefficient gamma is a complex value which have a magnitude gamma and phase phi. So it is a complex value with amplitude gamma and phase e to the power j phi. And effectively the value of gamma, or the amplitude of the reflection coefficient, is greater than 0 and less than unity. So it is a must to be less than unity. It cannot exceed unity. Okay. For the case of lossless media, in case of the lossless media, eta 2 and eta 1 are pure real. So in this case, if eta 2 is greater than eta 1, the phase would be 0. And if eta 2 is less than eta 1, the phase would be pi. Okay? That's what we are seeing. The ratio of the amplitude of the reflected and incident electric field is defined as the reflection coefficient. In a similar way, we can obtain the value of the transmitted electric field, which is Ex2 plus, over the value of the incident field. And if we remember, from the boundary condition of the tangential electric field, we found that Ex plus Ex minus in region 1 equal Ex2 plus in region 2. So effectively, if I'm interested in finding out Ex2 plus, it means that I should add here plus Ex1 plus 0. Or in other words, we can say that the transmission coefficient, which correspond to the value of the transmitted field to the value of the incident field, would equal 1 plus gamma. How it comes? Effectively, Ex2 plus, it can be represented as Ex1 plus Ex1 minus. So Ex1 plus over Ex1 plus is 1. And Ex1 minus over Ex1 plus, it is gamma. So effectively the transmission coefficient, which is the amplitude of the transmitted electric field to the incident electric field, would equal 1 plus the reflection coefficient gamma. And according to gamma it was eta 2 minus eta 1 over eta 2 plus eta 1. So if I'm going to replace gamma here by eta 2 minus eta 1 over eta 2 plus eta 1 and add 1, so the total summation, it would be 2 eta 2 over eta 1 plus eta 2, where eta 2 is the intrinsic impedance of the region 2 and eta 1 is the intrinsic impedance of region 1. And once again, these intrinsic impedances are in general for lossy media are complex values. So the transmission coefficient in general is a complex value which has an amplitude tau and phase phi transmission or phi t. So the transmission coefficient can represent as a magnitude of tau multiplied by phase e to the j power phi t or phi t. Okay. And as we say, the ratio of the amplitude of the transmitted and incident electric field are defined as the transmission coefficient. Alright? Okay.